now that we have the model of experience utility, we can model the behavior of the consumer as a utility maximization problem. One thing that you should keep aware is that this is a model of a rational consumer, and the consumer is rational in the sense that he knows its experience utility function and is gonna act either explicitly by thinking about it or implicitly somehow its psychological processes will guide him to choose the action that maximizes his well-being, his experience utility. Okay? Now, this consumer faces the following constraints, or has the following characteristics. Has an external amount W, which we are going to denote or call wealth, of this composite good M, and is allowed to buy any non-negative amount of good X at a fixed price P. Notice that there is an assumption here that is often called a price-taking hypothesis, which is that the consumer has no control over the price. It can only control how much it can consume. And the consumer can choose how much X it wants and how much M it wants, but notice that how much M it wants is just given by its total wealth minus the cost of buying the level of X that it wants. So in reality, we can make this a problem over a single maximization. Sorry, we can make this a problem over a single control variable, as we saw repeatedly in the previous unit. By the quasi-linearity assumption on the form of the experience utility function, this problem is just equivalent to maximizing over X non-negative the benefit function plus the total amount consumed of good M of the composite good, which is just W minus XP. Now, that's just replacing the functional form of the utility function. But we also see that we can drop the constant from any maximization problem, since it affects the total value of the experience utility that the subject gets, but it doesn't affect the optimal choice of X. So this is equivalent to maximizing over X greater than 0 B of X minus XP, where B of X is the benefit from consuming X units of good X, and this is the cost of buying them. So I hope that you see that the utility maximization problem, under the assumptions that we have created, has this familiar structure of a benefit minus a cost. Okay? Now, one piece of notation. We are going to denote the solution to the problem, the optimal choice, as a function of the price as X star of P. That is equal the optimal choice as a function of P, or for P, given P. But that's also going to be called the demand for good X at P. Now, as I mentioned before, the consumer in reality has to choose how much X and how much M he's going to consume. It's just that M happens residually. So notice that once we have X star of P, the amount of the composite good that he consumes is just given by the budget constraint, basically by W minus P X star of P. Is automatically follow from the nature of the problem. Now, what about the solution to the utility maximization problem? So recall that the problem looks like maximize over X greater or equal than 0 B of X minus X of P. Now, recall also that we have assumed that B prima is greater than 0 and B double prima is less than 0. Given the linearity of the cost function, this implies that the problem satisfies the concavity conditions are satisfied, and in that case we know a lot from unit 1 about the properties of the solution, and that's what I'm going to do now, is characterize them. In particular, we have to worry about 3 cases that I'm going to draw for you. Case 1 is the most interesting one in some sense, which is an interior solution. And this is a solution in particular where the demand at that price is greater than 0. Now, how do the first order conditions for this case, and in general the characterization of the solution, look? So we can do these first order condition maps or graphs that we were doing before, and it's going to be a case that looks like follows. We have at P, this is the X, a constant, what we were referring to before in the math section as a constant marginal cost. We're going to have a marginal benefit function that somehow crosses from above. So B prima of 0 is above P, and it eventually crosses. And we're going to have that the optimal level of demand is this given by the cross, X star of P. So in particular, X star of P is given by the solution to B prima of X equals P. That is the equation that determines the interior solution. Now, there is a second case that we also look at length in Unit 1, which is a corner solution with X star of P equals 0. And if you remember, that's a case that looks like this. We have the price, for example, here, which is the marginal cost. The marginal benefit function, B prima, crosses at 0 below. So in that particular case, it never paid off to take off the first unit, and the optimal solution is to set equals to 0. Now, unfortunately, since there is nothing in the model that guarantees that the crossing conditions are satisfied, we need to worry about a third case that looks like this. X star of P is equal to infinity. In some sense, the solution doesn't exist. And that's a case that looks like this. You have X, you have P, and you have a marginal benefit function above, but that somehow keeps going down but never crosses. It never crosses. Okay? So in this particular case, it is profitable in terms of increasing experience utility to keep doing the marginal, buying more and more of X on the margin all the way to infinity. And since we can spend as much money as we want, since the composite good M can go negative as much as necessary, that is feasible. Blah, 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 blah. Now, 2 additional things about the nature of the solution to the utility maximization problem. First is that for most utility functions that are used to model economic behavior, this case doesn't apply. And it doesn't apply because they tend to satisfy the crossing condition property, or something that generates a crossing condition, which is that B prima of infinity is equal to 0. In other words, this marginal benefit keeps going down, down, down to 0 for X sufficiently large. So in most examples that we're going to do, and in most applications of these models in economic analysis, this case is not interesting, and we're not going to basically look at it again. The other thing that I wanted to bring out, which is extremely important, is to highlight the economic intuition for the solution to the utility maximization problem. And of course, it's going to parallel the math that we saw in Unit 1, but there is something extra about economic intuition that is worth thinking. So think about what's going on. You start at 0, okay? And you can ask, a way of solving the optimal choice problem for X is to start at 0 and decide where to stop. Okay, so you can start at 0 and say, should I take the first unit? Well, if I do that, that increases my utility by the marginal utility of X at 0, which is this much, B prime of 0, and it only costs me P dollars. That decreases my consumption of the composite good by P, so my net increase in utility is by this. So when B prime of 0 is greater than P, I should do it. In this particular case, I should not do it because the loss in the composite good is more than the gain in utility. And clearly, I should keep doing that. I should keep increasing X as long as the marginal utility of increasing X exceeds the marginal cost, which is the loss in consumption on M at the margin. So I should keep going all the way to this. It's only at the point where the marginal benefit or the marginal utility of X is equal to the marginal cost that it generates, the loss in consumption of X, that you should not take the extra step of X. In this particular case, since the extra cost of X, of consuming X, keeps getting larger and larger by the decrease of B prime, you stop at 0 and you never go further. So the marginal benefit function is very important because it really measures the value of this additional unit. It really measures the value in terms of experience utility of consuming an additional unit of X. And P is very important because it measures the cost in terms of lost utility from consuming less M of buying an additional unit of P. And somehow the optimal solution involves balancing these two.